In this last lesson, we are going to talk about exponential equations and exponential models. So first, let's look at the graphs and equations of exponential functions. When we look at an exponential function, it's going to be either a growth or a decay. If it's a growth, that means as we trace it left to right, it's going to be going up. If it's a decay, that means it's going to go down left to right. Now, this piece here is going to continually get closer and closer to the x-axis, but it will never actually touch the x-axis. Now, when we're looking at an equation for exponential growth, this is what it looks like. Now, there's going to be another equation I introduce later, and both of them work fine. You just might use one over the other depending on the information that's given to you in the problem. So we're going to start off with this equation here. And this A represents the initial value, so whatever you're starting off with. This R represents your relative rate in decimal form. So, for example, if something is growing at a rate of, let's say, for example, 30%, then R is going to be 0.30 because you want to make sure that you write your percentage in decimal form when you plug it in for R. So R is your percentage or your relative rate in decimal form. Okay, and then your T is your time. Now, notice the difference between the exponential growth equation and the exponential decay. The only difference is that when we're growing by a certain rate, we're going to add the R. When you're decreasing by a certain rate, we're going to subtract the R. That's the only difference. Now, let's discuss the difference between exponential and linear. We know the difference in the way that the graphs look. Linear is just a straight line, and exponential has that curve that's either a growth or a decay. But when you're talking about in the context of a problem and you're trying to decide, do I need to model this with a linear equation or an exponential equation, the way that you can tell is the way that the problem states that the growth or the decay happens. So if the problem tells you that it's changing by the same absolute amount for every unit of time, then that's going to represent a linear model because it's a constant rate of change. It's going to change by the same absolute amount every unit of time. If we're talking about an exponential model, then it's going to change by the same relative amount every unit of time, meaning by a percentage each unit of time. So let's look at this first example. It says the population of a town is increasing by 669 people per year. This is a rate that is constant. It's increasing by an absolute amount per year, so per unit of time. It's not going to change from year to year. It's going to be exactly 669 people every year. We're going to state whether this growth is linear or exponential. So because this is changing by the same amount of people per year, that's an absolute amount, so we're going to say that this is linear. The absolute amount that it changes is that it grows by 669 people per year. Now, what will the population be in 3 years? Since it's linear, I know I'm going to use the model y equals mx plus b. My m is my slope, and that's the rate. That's my absolute constant rate that it changes every year. So that's going to go in here, 669. And then my b is my initial amount, and it says it starts at 2,000. So here's my equation or my model for this situation. So I have y is equal to 669x plus 2,000. The author of this question wants to know what will be the population in 3 years. Since y is going to be the number of people and x is the number of years, all I have to do is plug in 3 for x, and I'm going to get out 4,007 people. All right, let's look at this next example. It says, during the worst periods of hyperinflation in a certain country, the price of food increased at a rate of 25% per month. That is a relative increase. It's not an absolute. This is increasing by a percentage. So when you take a percentage of something, it could change depending on what the base is. So it's not an absolute amount. This is a relative change per unit of time, and the unit of time is month. Okay? So state whether this increase is linear or exponential. Because this is growing relatively, we're going to say that this is an exponential model, and the relative growth is 25% per month. So that means when I want to answer this second question, what will be the monthly food bill after 3 months, we need to use the exponential equation. So I'm going to use y is equal to a, and then inside I have 1 plus r. Now I'm using the plus r, not the minus r, because this is a growth. And then we're going to raise that to our unit of time. It tells us that our initial value is 125. Our rate in decimal form is 0.25. So I put that in for r. And then I still have this t here. So I'm going to carry over everything. I have 125. When I take 1 plus 0.25, that gives me inside the parentheses 1.25. And then I've got to raise that to my unit of time because they're asking me what the monthly food bill will be after 3 months. 3 is the month, so that goes in for time. And we need to round this to the nearest dollar. When we put this in on the calculator and round to the nearest dollar, we're going to get 244. Now, in case you're not sure how to use the exponent key on your calculator, let me show you. So to put this in on the calculator, I'm going to do 125 times 1.25, and then I'm going to use this little arrow right above my division sign to raise it to the power of 3. And then I can arrow over to drop back down and hit enter. So that will give me the 244.140625, and then because the directions say to round to the nearest dollar, our final answer would be 244. Okay, so now that we have an idea of the difference between linear and exponential growth, remember linear is an absolute change per unit of time, and exponential growth or decay is going to be a relative change per unit of time. That's the big difference. So we're going to talk about double time next. Now, when someone talks about double time, that means it's the time that it takes for the initial value to double. So in this example here, I just made up an example where I have time in minutes down here. I have 5 minutes, 10 minutes, 15 minutes, and 20 minutes. And then along the side here, I start at 1. That's my initial value because that's where it crosses the y-axis. And then I go up by units of 1 here. So at time equals to 0, I'm starting at 1 unit. That's right here. In 5 minutes, I have 2 units. And then if I come over to 10, I go up to 4. So in 10 minutes, I have 4 units. And then if I continue this pattern, if I go up to 15, I would go to 8 units. What this tells me is that the double time is 5 minutes. Because if you notice, every 5 minutes that pass, my amount is doubling. So I go from 1 to 2, that's doubling. Then in the next 5 minutes, I go from 2 to 4, that's doubling. And then in the next 5 minutes, I go from 4 to 8. So this is the whole concept of double time. So I would say that every 5 minutes, my amount doubles of whatever it is that you're talking about in the context of the problem. So now that you understand what double time is, I can introduce to you what this equation is here. This is now a second equation that we have in our toolbox that we can use for exponential models. So the equation is y equals a, which is our initial value, times 2 to the power of t divided by dt. T is just the time that has passed, and dt represents the double time. So in this case, if I was trying to calculate something, I would put in 5 minutes for double time. Now, one thing I need to stress is that this t and this dt need to have the same units. In other words, if double time is listed as minutes, then when you put in your time t here to see how much time has passed, then that t has to be in minutes as well. So these two need to remain the same units. So in this next example, it says the doubling time of a population of flies is 4 hours. That means every 4 hours, the population doubles. It says, by what factor does the population increase in 20 hours? So let's make a table of values here. Now, I recognize that I can make a table of values here because 4 divides into 20 evenly. So I'll be able to just make a table and then look at what my factor is at 20 hours. But I'm actually going to show you another way to do that as well in the next part. So my double time is 4 hours, and A is my initial value at 0 hours. So in 4 hours, if I start with A, that means I'm going to end up with 2A because it's going to double, right? From 0 to 4, that's 4 hours, so A is going to double to be 2A. Then if 4 hours passes again, so now I'm at 8 hours, that means this 2A is going to double. So 2A and 2A is 4A, so that gives me double again. If another 4 hours pass and I go from 8 to 12, then 4A is double and it becomes 8A. Then if it doubles again and 4 hours pass again from 12 to 16, then 8A is going to double and become 16A. And then our last double time, if I go from 16 to 20, that's another 4 hours, so it doubles again. Here is my last double time. So at 20 hours, 16A changes into 32A. So this is going to be a factor of 32. So whatever I started with, it's going to increase by a factor of 32. Now, I want you to keep in mind that 32 can be written as 2 to the 5th, and this is going to play into the other way that you can do it. So, in the next part of this example, it says, by what factor does the population increase in 3 weeks? Well, this isn't as nice as 20 hours where it'd be easy to make a chart. So if this isn't, the time that's given isn't in a nice way to make a chart, then I suggest using the formula. So our double time formula, when we're dealing with the exponentials, is y is equal to a times 2 to the power of the time that passes divided by the double time. In this case, the double time is 4, so I'm going to put that in. dt, our double time is 4, so I put that in here. But where am I getting this 504 from? Remember I said it's really important to make sure that the t and the dt have the same units. The double time is given in hours, and they're asking us to see what happens in 3 weeks. So these units don't match up. So I need to change weeks into hours, and that's where I'm getting the 504 from. So now that I changed it so that it has the same units, 504 hours, and then 4 hours down here for the double time, I put all of this into my formula. So I ended up getting a times 2 to the power of 126, and I got this 126 by taking 504 divided by 4. And so if I started with some amount A and I ended up with A times 2 to the power of 126, then that means I increased by a factor of 2 to the power of 126. Now, I don't plan on actually multiplying this out because it's a super big number, and I'm going to leave it as just 2 to the 126. But now I want to point out why I emphasize this 2 to the 5th here. Instead of doing this table format where I just kept doubling until I got to 20, if I use this formula rather than the table format, what I would have done is plugged in 20 hours for t right here, and dt would have been 4 hours, my double time. So I would have gotten 20 over 4, which is 5 when I divide. So I would have ended up with a times 2 to the 5th. And that's this here, which is the same thing if we multiply it out as 32. So there are times when you can use a table, and if you want, you can use the formula as well to double check it. In the next example, we have the initial population of a town is 6,200, and it grows with a doubling time of 15 years. Determine how long it will take for the population to quadruple. Quadruple means it grows by a factor of 4. So if it starts at 6,200, we want to see how long it takes to get to 6,200 times 4, which is 24,800. So if I start at time 0, I end up, I have 6,200. That's my initial value. Now, if I go from 0 to 15 years, that means it's doubled. So I go from 6,200 to doubling to 12,400. From here to here, it doubles because I went 15 years, which is a doubling time. Then if I do another doubling time from 15 to 30 years, I double this 12,400 again, which gives me this 24,800. And that's what we were looking for, how long it took to quadruple. So it took 30 years to quadruple. Now, another way to look at that is if it quadruples, that means it doubles twice, which means I have 2 doubling times, which means 15 and 15, which will be 30 years. So that's another way you can look at it if you can do that quickly in your head. Now, looking at this bottom example on page 3, it says the initial population of a town is 5,800, and it grows with a doubling time of 11 years. What will the population be in 14 years? Round to the nearest person. So if we start off using the table method, at t equals 0, I'm starting at a population of 5,800. Every 11 years it doubles. So when I hit 11 years, t is equal to 11, 5,800 is going to double, and I'm going to get 11,600. If it doubles again, that means I'm going to reach 22 years because it's going to go another 11 years, which means 11,600 is goes in 200. Now, when I use the table method here, since 11 doesn't divide into 14 evenly, that doesn't give me what the population is in 14 years. But by setting up this table, I have an idea of what it should be. I know 14 years is going to fall between these two numbers, right? Between 11 years and 22 years. So if I use the formula, my answer better come out between these two values. So it's a way that I can check to make sure my answer makes sense. So now, relying on the formula, here's our formula. We have y is equal to a, our initial value, times 2 to the power of our time divided by our double time. So I'm going to take 5,800 times 2. The time that we're looking for that passes is 14 years. So I'm going to put that in for the t. My double time that's going to go in the denominator is 11, and I'm going to work that out on the calculator. Now, the question says round to the nearest person. So on the calculator, I'm going to put 5,800, that's my initial value, times 2 to the power of, now this 14 divided by 11 should all be in the exponent. So I'm going to put parentheses around it and put 14 divided by 11 and close parentheses. Then I'm going to arrow over to drop down. And this is where I'm getting this number right here. So I have 14013.83756. But to round it to the nearest person, since this is a 0.8, this 3 is going to jump up to a 4. So my final answer is going to be 14,014 people, which definitely falls between 11,600 and 23,200. That definitely falls between these two values, so my answer makes sense, and it's a way that I can double check myself. Now this is going to be our last double time question, and then we're going to jump into half-life, which is a very similar concept. In this example, it says the number of cells in a tumor doubles every 3.5 months. If the tumor begins with a single cell, how many cells will there be after 3 years? So to figure out after 3 years first, the first thing we need to notice is that the units for the double time is in months. However, they're asking us to find it in 3 years, so the units don't match up. So we need to change 3 years into months. So that would be 36 months. So I want to plug in 36 for my t, 3.5 for my double time, and then it says I start with 1 cell, so that would be 1 here, my initial value. It also says do not round until the final answer. So in other words, we don't want to figure this out first, round it, and then round again at the end, because when you round multiple times, it will throw off your answer. So we want to put all of this in the calculator at once and do the calculation 1 time and round just at the end. So on the calculator, I'm going to take 1 times 2 to the power, and then 36 divided by 3.5 is all in the exponent. So I want to make sure I put parentheses around that. 36 divided by 3.5. That's all in the exponent. So I'm going to drop down and hit enter, and it's going to tell me that my answer is 1,248.269982. Now it says round to the nearest whole number, and because this is a 2, we're going to keep that at an 8. So my final answer is going to be 1,248 cells. Now we're going to do exactly the same thing here when we calculate it after 5 years. 5 years in terms of months is going to be 60 months. So I'm going to put 60 in here for time and go through that same process. And we'll find that there's 144,715 cells after we round it to the nearest whole number. Now let's talk about half-life. Half-life is the time it takes for something to decay to half the initial value. So before, when we talked about double time, things would double, which means we would have exponential growth, which means when we looked at the graph, it would be increasing left to right. So now we're looking at things getting cut in half, so we're talking about decay, which means when we look at the graph, it's going to go down left to right. So I made a similar example as I did with the double time, showing the graph and how things get cut in half instead of doubled. I started here at time 0 at 8, and we kept cutting it down every 5 minutes, which is how we get this half-life of 5 minutes. So let's walk through that. I have 5, 10, 15, 20 minutes on my x-axis, and then I scaled it by 1s on the y-axis. And our initial value, I had it set at 8 units. Whatever it is that we're talking about, it crosses the y-axis here at 8. In 5 minutes, it gets cut in half from 8 units to 4 units. So at 5 minutes, it's going to go from 8 to 4. Then in another 5 minutes, let's see, we did 5. So in another 5 minutes here, so that would be 10 minutes, that 4 units is going to get cut in half to 2 units. So that's going to be here. Then it's going to get cut in half again after 5 minutes. So that would be 1. And then again in 5 minutes, it's going to get cut down to a half unit. And you can see it's going to get closer and closer to the x-axis because it's going to keep getting cut in half. So theoretically, since it keeps getting cut in half, it's never actually going to touch the x-axis. Now, the equation that we want to use when we're dealing with half-life and we're looking for an exponential equation, it's very, very similar to the double time equation. You still have this initial value here, but since we're talking about half-life, this is going to be 1/2 instead of 2. Here's the time that passes, and then instead of having double time here, we're going to have half-life here. All right, let's walk through our first example using the half-life formula. It says the half-life of a drug in the bloodstream is 26 hours. What fraction, written as a decimal, of the original drug dose remains in 24 hours or in 60 hours? And again, we're not going to round until we get to the final answer. It says round to the nearest hundredth. Okay, so it tells us that the half-life is 26 hours. Our formula is y equals a times 1/2, and then t, the time that has passed, goes on top, and then the half-life goes on bottom. Since they're asking to see what is left after 24 hours, that's the time that has passed, so that goes up here, and the half-life is 26. Since 24 hours has passed, which isn't quite the half-life, it's going to be a little bit more than half that should be left if we use our noggin. Once we reach 26 hours, then we know it's going to get cut in half. But we're not quite there, but it should be close to half, but not quite. So when we put this in on the calculator, we take 1/2 raised to the power of 24 divided by 26, remembering that this whole thing is in your exponent. So make sure you put parentheses around that. You should get whatever your initial value is, a, times 0.5273830,382. Now, it says to round your final answer to 2 places. That's the hundredths place. So when I round this to 2 places, that gives me 0.53. So that means whatever I started with A, I got 0.53 left of A, which is a little bit more than 50%, which makes sense because we haven't actually reached that halftime yet. We're close, but not quite. So we're going to say that we have a factor of 0.53 that's left. Now we're going to do the same thing for 60 hours. We'll put 60 up here. Now that's more than 2 half-lives. So it should be less than 1/4 left. So we have a half raised to the power of 60 over 26, which gives us, when we raise that half to 60 divided by 26, we get 0.201983268. Rounding our final answer to 2 places, we get 0.20, which is less than 1/4 left, which is what we suspected. So our factor is going to be 0.20. All right, let's look at our second example with half-life. It says the current population of a threatened animal species is 1.4 million, but is declining with a half-life of 25 years. How many animals will be left in 40 years or 50 years? And we're going to round to the nearest whole number. So the question tells us that we have a half-life of 25 years. So when we're dealing with half-life and we want an exponential equation, we're going to use the one that has a half in it. So we're going to have y equals a times 1/2 to the power of t over the half-life. Now they tell us in the question that we're starting with 1.4 million animals, so that's going to go here. 1/2 just gets carried down. Now, because these units are the same, I don't have to worry about changing unit. These are both in years, so I'm good there. I don't have to change units. Now, when I put this in on my calculator, I'm going to get 461,827.7688, and then we've got to round it to the nearest whole number. Now, when you put this in on your calculator, remember that this is in millions. It's not 1.4, it's 1.4 million. So when you put it in on your calculator, make sure you put in 1.4 E6, because remember, E6 means times 10 to the 6th, which is in millions. And that E, if you recall, is this double E here from scientific notation. It's right above your comma. So it shows up on your keypad as a double E, but when you push it, it comes up on your screen as a single E for your scientific notation E. Now, for this one here, we're going to do the same thing, but now we're using 50 years. So the same exact formula, but we're plugging in 50 here instead of 40. When we work that out on the calculator, we're going to have 350,000 animals. Now, if you notice, 50 is divisible by 25. So I have 25 and then 25 to make 50. That's 2 half-lives. So another way you could do it other than using the formula is you could make a table, since this comes out nicely. You start with 1.4 million. When you pass after the 25 years, you get 700,000 because you take 1.4 million and divide by 2. Then when another 25 years have passed, that gives you a total of 50 years. You get cut in half again, so 700,000 divided by 2 is 350,000. So here's a second way to do it using a table, since 25 goes into 50 evenly. So this is a nice way you can check to make sure what you're doing makes sense. Now, up to this point, in all the examples, we have been given the half-life or the double time. Now we're going to actually walk through on how you can find those values for yourself. To find the half-life, you're going to take the log of a half and divide by the log of 1 minus r. To find the double time, you're going to take the log of 2 and divide by the log of 1 plus r. And your log button, if you're not sure where it is, it's right to the left of your 7 on your keypad. So if you look to the left of your 7, it says LOG. That's your log button. So let me walk you through how we use these formulas. It says an urban encroachment is causing the area of a forest to decline at the rate of 8% per year. So here's a key word. We're talking about declining. So we're talking about exponential decay, which also means we're going to be talking about half-life. Okay, the rate of decay is 8%. What is the half-life of the forest? And we're going to round to 100th of a year, so that means 2 places. So we need to find the half-life, so we take the log of 1/2 divided by the log of 1 minus r. Now remember, r is the rate in decimal form. So 8% as a decimal is 0.08. So when we clean this up a little bit, we're going to take the log of a half and we're going to divide by the log of 0.92. And I'm getting this 0.92 because I took 1 minus 0.08. So on the calculator, I'm going to hit log of a half, which is 0.5, log of a half, divided by the log of 0.92. Now, if your calculator has open parentheses, I suggest you close them, because some models, if you don't close it, will affect your answer. Then I'm going to hit enter, and it's going to give me 8.312950414 years. And the question says to round it to the nearest hundredth, so we're going to round to 8.31 years. So the half-life for this forest is 8.31 years. Now, the second part of this question says, what portion of the forest will remain in 20 years? So we're just going to use our exponential equation with a half in it, because we're talking about decay, and we're going to plug in the time for 20 years, and now we know what the half-life is, so we can plug that in for our HL in the denominator. So here's the equation we're using. We have the initial value times 1/2 raised to the power of the time that has passed divided by the half-life. So I'm going to plug all of that in, and when I put in the calculator a half raised to the power of 20 divided by 8.31, and we get 0.189a, which means if we start with a and we end up with 0.189a, our factor would be 0.189. Now, another way that we can do this is using the formula that we went over at the very beginning of this lesson. So when we have decay, exponential decay, we could use the formula y equals a, and then in parentheses we have 1 minus r raised to the t. We only introduced this formula after we talked about half-life. So if I use this formula, I should still get the same answer. I'm going to leave a alone because we don't know what a is, but I'm going to put in, let's see, it was 0.08 for r. So I'm going to get 1 minus 0.08, which leaves me with 0.92 raised to the power of t, and t is 20 years. So I put 20 in here, and when I work that out, and I take 0.92 raised to the 20th, I get 0.189 times a, which would also give us a factor of 0.189. So as you can see, you can use this formula or this formula, and you're still going to get the same answer. However, keep in mind that when you're using this formula, the 8.31 is rounded from our previous answer up here. So if these answers come out a little bit different, it's because this has been rounded. Now let's do an example of finding double time. A nation of 5 million people is growing at a rate of 6% per year. What is the doubling time of the population? And we're going to round to the nearest hundredth of a year. So here's our double time formula to find our double time. We take the log of 2 and we divide by the log of 1 plus r. Now we're using plus because it's double time and we're talking about growth. My rate is 6%, but when we put it in decimal form, it's going to be 0.06. So we're going to take log of 2 divided by the log of 1.06. Now, when we do that, I'm going to hit the log button, and I'm going to hit 2 and close parentheses, and I'm going to divide by the log of 1.06, close parentheses. And this is what I get. I get 11.89566,105. Now the problem says round it to the nearest hundredth, which is 11.9. I'm going to take this entire answer that we just got, all the decimal places, and I'm going to save it in my variable x. So I'm going to hit this store button, STO. I'm going to hit that. I'm going to take my answer and I'm going to store it in x. So I'm taking all of those decimal values and I'm saving them. You'll see why in just a minute. Okay, now in this part 2, it says, what will be the population in 20 years? Answer in millions rounded to the nearest whole number. So because we're talking about double time, I could use one of two formulas. I could use this formula here, which is y equals a times 2. to the power of t divided by double time, or I could use this formula from the beginning of the lesson that we used before we got this formula. Either one will work. Okay, so let's do one at a time. So it says our beginning value is 5 million. And now it says to answer in millions, so I don't have to put in 5 million. I can just put 5. We're going to leave it in millions. So in the calculator, I'm going to put 5 times 2 to the power of 20 divided by 11.9, because 11.9 is our double time that we got from this part up here. So I'm going to take 5 times 2 to the power of 20 divided by 11.9. I'm going to hit enter, and I'm going to get 16.02886496. That's what we got here. And then it says to round to the nearest million, so I'm going to put 16 million as my final answer. Now, when I use this formula here, I'm going to put in my rate of growth. They said that at the beginning. Let me scroll back up to show you. Up at the beginning, it says the growth rate is 6%. So I'm going to put in 0.06 in for this R. So I'm going to get 5 million times 1.06 raised to the t, and the t, they said, is 20 years. Now remember, again, they want the answer in millions so that I don't have to actually do 5e6. I can just put in 5. When we do that, I get 16.035677736. So if you notice, these are a little bit different. Why are they different? Right? I said that you should come out with the same answer. Now when we round it, we come out with the same answer, but look, before we round it, look at they're different. The answer is because, remember up here in part A, when we found that double time, we rounded. So because we rounded this, our answer came out a little bit different on this one. So this is the more accurate value. So watch, if I put in, instead of putting in 11.9, if I put in all the digits and I don't round it, I should get the same thing. So I'm going to do 5 times 2 to the power of 20 divided by, now remember I saved all of those digits in x. So I'm going to put 20 divided by x because all of those digits I saved in that x. Now look at, so I have 16.03567736, which is exactly what we got right here. So this is off because we rounded that 11.9. So keep that in mind. If you're using the double time or the half time and you've rounded that, your answer is going to come out a little bit different. Okay, we've got one more double time example, and then we are going to jump into our last topic, which is exponential regression. So we have a family of 100 termites that invades your house, and its population increases at a rate of 21% per week. So our unit of time is in weeks. What is the doubling time of the population? And we're going to round to the nearest hundredth of a week. Okay, so our double time formula is log of 2 divided by log of 1 plus r. The value of r is 0.21 because it's 21%. We've got to put that in decimal form. So we're going to take the log of 2 divided by the log of 1.21, and we're going to get 3.636270449 weeks. And then when we round it to 2 places, we get 3.64 weeks. Now, the second part says, what will be the population in 1 year, which is 52 weeks. Remember, we got to keep the time unit the same. And we're going to round our answer to the nearest whole number. Well, we have our two formulas, here and here. Here's our double time exponential formula. We have y equals a, which in this case, we're starting with 100. So I put 100 in here. So we have 100 times 2 to the power of 52 weeks, because that's equivalent to 1 year. We need to make sure that our units stay the same. And we're going to divide by our double time, which we found up here in part A, which is 3.64. Now remember, this value was rounded. So this answer here is going to be a little bit off. So when we put that in the calculator, we get 1997231.971. And when we round it to the nearest termite, this 9 makes this one bump up to a 2. Now, when we use this formula here, we put in 100 for our initial value. We use 1 plus r because this is a growth function. So I'm going to take 1 plus 0.21. That's going to go in here, and then I'm going to raise it to our time, which is 1 year, but we have to put it in terms of weeks. So that's 52 weeks. And when we put that in on the calculator, we get 2017619.453. Now, when we round that to the number of termites, this 4 is less than 5, so this 9 is going to stay the same. So our answer using this formula is 2017619 termites. Now, when you're using XYZ, it's programmed to accept either one of these answers, because we know that in part A, we told you to round it to 3.64. So it will accept either this answer or this answer. But remember, the reason for that discrepancy is because this 3.64 was rounded up here. So I suggest, just for practice as an exercise, to use what I did in the previous example by storing all the values and putting all the values in here and making sure that you get the same answer that way. It's a good exercise to convince yourself that the difference is this rounding error here. Okay, our last topic is exponential regression. And this is a similar process as to the linear regression that we covered in the last section. We're going to have a plot of data, a scatter plot, and we want to try to fit a curve or a line the closest that we can get to the points on that plot. Now, when that plot has a curve to it so that it looks like an exponential curve, we want to come up with an exponential model or an exponential equation to try to get the closest that we can to all of those points. So what we're going to do is we're going to start off by reading the problem and plotting this data, and then I'm going to walk you through the procedure on how to find an exponential equation using that regression procedure. So this says the table below shows the number of individuals infected with the disease T days after it was first detected by the CDC. So this is the number of days, and this is the number of individuals that are infected with this disease. So to plot our data, just like we did with linear regression, we're going to do the same thing. I'm going to hit the stat button. And to put the data in, I'm going to hit enter on edit. Now, if you have something already in there, to clear it, you're going to highlight the list that you want to clear, and then you're going to hit clear, enter, and it will clear the whole list. And then you can put your values in. Your X's should go in L1 and your Y's should go in L2. So let's see, it looks like it's just the days 1 through 8 for X's. And I already put my Y values in there previously to save a little bit of time. If you need more time to enter the data, just pause the video for a moment. Once you have all that data in there and you double checked it to make sure it's correct, you want to hit second y equals, and you want to make sure that your first plot is set up correctly. You want to make sure that it says on. So you want to make sure this says on. You want to make sure that it's on scatter plot, and you also want to make sure that your x and your y list is L1 and L2. Once you do that, you can hit zoom and then option 9, and that way it will set up the window for you. Now, these data values, if I imagine a growth curve passing through those points, that would probably be a really good fit. All right, now that we see what the graph looks like, and we know that we want to use an exponential function to model this data because it looks like it has a nice exponential curve, what we're going to do next is we're going to hit the stat button. This time we're going to arrow over to calculate. And before we used option number 4 that says linreg for linear regression, but now we are going to scroll down and look for exponential regression, which on my calculator is option 0 right here. So I'm going to hit enter, and then I'm going to tell the calculator where my x's and y's are stored. My x's are in L1, my y's are in L2. Frequency list and storing your regression equation, just leave those blank. And I'm going to click on calculate. Now, if you have the other model calculator where when you click on exponential regression and it comes up on your home screen, just make sure you hit L1, L2 after it says linear regression, and then hit enter, and you should still get the same answer. Okay, so the calculator uses the general form a times b to the power of x. Now we've used t for time because most of the time this is t for time, but just know that that's our variable. It's just a different label. So they're telling us our a, which is our initial value that goes in front, is 642.7850021. And our b, which is what is going to be the base for our t, is 1.465906283. Now the question says when we write our regression equation to list out 3 decimal places. So when I rounded, I have A is 642.785 and B is 1.466. So my equation is going to be 642.785 times 1.466 raised to the t. Now it says use the model to predict the number of individuals infected with the disease after 18 days. So that means we're going to plug in 18 for t and figure out what we get for the number of people. So I'm going to put in my calculator 642.785 times b, which is 1.466 raised to the power of 18, and it's going to give me 628,748.8432, and when we round it to the nearest whole person, because we don't want a portion of a person, this 8 right here is going to make this bump up to 9. So our final answer is going to be 628,749. Now, just like before, if you want to see your curve overlap with the points to see how good the fit is, we can go to y equals and put our equation in here. Now, if you have something already in there, you can just hit clear. So I'm going to put in there our regression equation, which we got was 642.785 times 1.466, and that's raised to the power of our variable. We're going to use our variable button, remember. That's this, not x the multiplication or x the letter. Make sure you're using this variable. then when we hit graph, it should show both at the same time. Now this looks like a really good fit. The curve that we're using to estimate this points goes through or comes super close to all these points. So if I stick to this area right here and I use that equation to make an estimate, it should be a really good estimate.